In this morning session, Dr. Griffin also briefly mentioned about this, and also Dr. Kajita, he showed us some work about the falling and failure of the humanoids. So I'm very pleased to hear and see that. But this research topic itself is relatively rare. Um, Actually, Dr. Kajita may know very well the reason, since he's the one of the pioneers of robot falling research. So um, I think the reason is um, we don't want the robot fail. So that's the reason why this research is so rare. Anyway, in fact, this kind of failure is inevitable. And in DARPA Robotics Challenge final, I was a member of a workman team in IIT, and as the others experienced, our robot had several falls and during the trial, and you have watched it in many DRC videos, where you see different types of the fallover in this video, and even in the same robot. One was almost like a free fall on the top video. It was happening during first trial because of power cut. And the other fall at the bottom, um, that fall happening in the second trial. And actually, it was still controlled, but it just fall over, just lose its balance. In fact, the first one didn't damage the robot so much, and we could operate the robot again for the second trial. But the second fall indeed break some of the encoders, as well as made a lot of scars on the robot. And in fact, in this case, since the robot was still in control, so it could do some reaction to cope with this fall. But of course, we were not ready to do it, and like many others. So after this, naturally, I started to think what would be good falling, and I mean, some reduce the damage and just keep our operation for the robot, something like that. Um, so here so after that I tried to somehow summarize the works from 2000, even 1995. There was a really starting work about the falling over of the robots. And this graph indicates those paper publications in last 2 decades. So in total, uh, this topic, um, the papers less than 100 papers, um, which are directly dealing with humanoid fall. And it's quite interesting that there was a big rise after 2015. It's very obvious just after DARPA Robotics Challenge. And those papers cover not only fallover control, but also falling prediction, modeling, and active and passive protection developments, and recovery control from the fall, something like that. So in this talk, among those topics on post-fallover, I would like to briefly introduce a real-time fallover control and recovery strategy. To go further, I would like to begin with the term break fall. Actually, that is a general term which describes the movement performed to prevent injuries when falling or landing. So the break falls were designed by martial artists so that they could practice their techniques without hurting each other. In Japan, the term is ukemi. I think that is more general term. It's well known in martial arts aikido. So even you can also find this breakfall technique in many other places. For example, in military drill, you see the video on right top, some parachute landing drill, and on the bottom, some parkour. You see forward and backward fall, and there are extreme cases, but they are all break fall. So this is not an ordinary falling, but this is all for the training and learning how to fall. So it's very obvious that the robot should be trained like human, that is control fall for humanoids. So the question is how to generate whole body motion during the fall over, exploiting break fall techniques. By simple observation here, the videos, you found two main movements. So basically, one is lowering the body height, it's very basic, and rolling. So this means we human try to reduce the total energy, that is energy shaping. And rolling motion can distribute the energy to multiple contact points and dissipate it by switching the one's momentum into rotational energy. In some cases, this momentum can be created upon landing by diving into roll, even from a vertical drop. So I'll address this later as energy injection. For energy shaping, we use a simple LIPM model, LIPM, since it can present both tipping and COG lowering motion of the humanoids very well. I'm not going to go into detail, but the principle of this controller is to monitor the energy of the system online and generate control input to regulate the system to the desired energy level. So from this energy control low, their blue color, you see that one can compute the difference between initial and the desired energy obtained like E tilde. And with the suitable control input, if you design R underscore D, RD, the derivative of E tilde can be made negative, which ensures the energy of the system decreases always. The control input RD is used for then actuating the center of gravity in a whole body motion. So with the energy shaping, the controller minimizes the energy, of course, and hence lowering the body and then lowering the impact forces. As you can see here, the LIPM motion from the energy shaping. The beginning, because potential energy is very high, it tries to bring it down as fast as possible, resulting the squatting motion in humanoid body. And near the end, the kinetic energy starts increasing. So the control low generates a stretching motion naturally in humanoid body. And that is the energy shaping part. But apart from the energy minimization, distribution is also very important. So this distribution is basically made by continuous contacts, that is the rolling motion. The humanoid can be presented as a segmented planar model. Here I'm just saying SPR. Formed with a context in interest to the controller. That means the point of interest could be hand or elbow or knee or some other places. So this model can be used to represent the rolling of the humanoid robot in 2D, but also you can extend it to 3D space with a polyhedral model. Here, the video at the bottom. So when we looking into the energy in rolling, basically we can get some insights from a very ideal condition of the circular shape rolling. So if we just assume ideal rolling, like non-slippery condition, basically there's no loss of energy. So once we inject the energy, then basically roll kind of object will continuously roll. But in the case of polygon, that is the model of humanoids in this case, there is a definite loss of the energy. So depending on the restitution of coefficient at every contact due to the impact. So energy injection is needed to ensure the rolling of the system over multiple contacts. So it's quite interesting point because when we try to reduce the impact, we try to reduce the energy, but to create a more context, then we can make a more distribution of the energy, then that eventually can reduce the impact forces. So we did a very simple simulations, and even we confirmed some of the energy injection can make the system rolling. And then this injection energy, the energy injection control is to monitor the energy state in online like before, and to compute the desired energy to make a sufficient rolling. And then basically from the equation at the bottom, we can generate the COG velocity command for making more rolling motion in the humanoid robot. So from the energy shaping control and the this energy injection control and rolling energy distribution, basically we can make a whole body controller like this block diagram. So first we can make a command of the center of gravity from energy injection and shaping control, and then bring it to the whole body inverse kinematic solver. So basically this whole body controller is position-based control. But it's quite efficient to generate the rolling motion as well as reducing the total energy. So here the simulation is done with just falling. It's a free falling condition. And when we use the energy shaping control, there is already certain differences. Basically, if you shaping the energy, you already get a 60% less impact forces. But as you see here at the bottom, if you make more contacts, then energy is distributed, and then the maximum impact forces is decreasing. And if you make a rolling motion, then as you see in this figure, you got like 30% less impact forces indeed. So we implement this controller on the other robots. Basically, we couldn't experiment on the real hardware because it has some real difficulty. So we just do some simulations. But the same controller can be applied to the other robots. But falling controller is general control framework to handle arbitrary directional falls, and online applicable and adaptable controller according to the disturbances we just confirmed. And let me quickly move on to the dynamic standing up problem as one of the possible actions. We want to deal with the situation where the robot is impossible to stand up by static motion due to the range of motion, or some needs of quicker recovery from the resting posture. So there were quite interesting studies from Professor Yohei in Tokyo University, and video from Boston Dynamics, and also you saw some video from Dr. Kajita in his talk. There are some studies, but here our goal is to develop a generic whole body controller for agile standing up. So for this, the first goal is to control the ground projected position of the center of mass, um, driving into the boundary of the support polygon of the feet with sufficient height from the ground, as well as guaranteeing stable contacts at the feet. And for more agility, rising motion should be made by pushing forces from the contact. Similar to the previous falling over control, we develop energy-based approach with state motion. So here you see pushing and rising and stand up, three very intuitive phases we can have. Basically, we differently control the center of mass motion, and then we could make an agile standing up motion with a whole body dynamics. Um, actually, to make a dynamic whole body motion with multi-contacts, basically we have to make the robot satisfy all the inequality constraints. So we develop a QP-based optimization with operational space-based whole body controller. The energy controller itself is quite simple, but works differently in each phase. So in the pushing phase, basically the controller produces a sufficient kinetic energy and potential energy by crouch motion. And then a rising phase, after making a pushing force, then kinetic energy is translated into potential energy with dedication by commanding center of pressure. And then after rising out, then basically we can just stabilize the robot. So you can use any type of the stabilizer. And in this case, we just use a capture point to stabilize the COM motion. To create whole body motion, that would be a big question, is because this problem is not that easy, because we have a multiple context, and then we have three different phases. So we decided to use the operational space-based whole body controller. It's because it's very effective to control hierarchical tasks for robot with redundancy and multiple, there should be multiple tasks. And also it can deal with multiple contexts, and it guarantees dynamic consistency. That is really good property for this kind of control. But there are some big difficulties to handle inequality constraints in this original form of operational space formulation. And also it takes a lot of computation to get on dynamic parameters. So we developed a new framework that is an enhanced framework of the conventional operational space formulation, combining with an QP optimization. Basically, the hurdle is the computation, because you see here in the block diagram, there is a contact constraint operational space dynamics that does several inverse of the huge matrices, and then that takes much time to compute those kind of dynamics parameter. So we develop multi-threading technique. Actually, we just use a multi-threaded technique, and then in the hard real-time thread, we do all the sensory data acquisition and state estimation, communication, low-level control, and high-level control with a QP optimization. And then in a separate thread, there's a non-real-time thread. Then we just do an inverse dynamics parameter computing there. And with the shared memory, we can share the information from the dynamic parameter to the hard real-time loop. And then the overall control structure is like this. So when we get the multi-body dynamics model from the robot, then basically the energy-based COM motion controller is working for 3 different phases, and then basically giving a command to the whole body motion controller as a COM acceleration. So this is a simple study from lean posture to standing. As you see here, the robot has 4 contact points, and you have to deal with this force distribution to make a proper force to push. So from the pushing phase and rising phase and stabilizing phase, the controller is working properly with the energy concept. And we also try to do the same controller on different postures, like lean to the wall with a more contact, and also different posture like sit to stand cases, all works pretty well. So we're saying this is kind of generic dynamic controller for standing up scenario. So I just conclude my talk here, saying challenges and open issues. Basically, to realize this kind of post-falling over controllers, there are so many things remained. And for example, simple state estimation sometimes is not really perfect, and it does make a lot of difficulties in implementation. And falling definition, basically, when we define the falling itself, it's a little unclear, because even for human, we can somehow overcome the falling in a certain condition. Then can we say that is falling or not? And in the case, our prediction should predict that reaction or not. And when we have to trigger our falling over control, something like that. And we need a very good environmental perception, and also we need a kind of decision making that is related to the falling definition. And also we need a good actuation for agile reflex motion and post-impact endurance and hardware failure. And when we get a hardware failure, then how we can detect that, and still we have a sensing or not, or how do we control that failed actuators and so on. So to bridge the gap between reality, of course, we need more study. And I personally wish this graph after 2019 is going up again. Yeah. That's all. Thank you.